So if you throw a third plane into the mix, it adds an extra way that the planes can interact, in that they can intersect on a single point instead of just on a line. So if we just take a look, and we'll go through each of the ways that these planes can interact. This first example, if you notice, 1, 2, 3, 4, it has been doubled and then it has been tripled. If I were to run this through my Gauss-Jordan elimination, I would end up with one row and then 2 rows of zeros. So just, I guess I should do that just to show you. We keep R1, that'll be 1, 2, 3, 4. And then if I do R2 minus 2 R1s, 2 minus 2 would be gone, 4 minus 4 would be gone, 6 minus 6 is gone, and 8 minus 4 is gone. And then I'm going to do R3 minus 3 R1s, and I'll get 0, 0, 0, 0 again. So in this particular instance, I've ended up with 3 coplanar equations. So if this happens to you, that everything drops out, these are all the same plane. And you maybe could spot that just looking at the equations. You didn't actually have to put them in the matrix to do it. These are all the same plane. So if I were to go and I was to change one number on one of these equations, like maybe this one, that's going to change my outcome a little bit. So when I do my Gauss-Jordan elimination, row 2 minus 2 row 1s, that would still be 0. That's still 0. That's still 0. But 9 minus 8 is 1. So I've generated an impossible row. And if that happens to you, that you've generated an impossible row where 0 x's and 0 y's and 0 z's are supposed to add up to any non-zero number, then you've determined that they don't intersect. So in this particular case, you have to do a little thinking to figure out how they intersect. If their normals are all the same, but they don't intersect, they must be parallel. So in this particular example, because the normals are proportional, normal vectors are proportional. But there is no intersection. Intersection fails. These planes must be parallel. This is a lot of things to write. Okay, so because this is double that, this is double that, this is double this, but then this is the only number that fails, the orientation of these planes is the same, but they've been offset, right? By adding that extra 1 to that number has lifted the one plane off of the other. So they are parallel, thus they don't intersect. So I'm going to erase this, and we're going to try another one. All right, so in this one, I have 3 planes, and the first thing I want you to notice is that 1, 2, 3 is very similar to 3, 6, 9, right? This normal down here is just triple that one. So maybe they're coplanar. Well, you have to check the last number. 3 times this is 3, 3 times this is 6, 3 times this is 9, 3 times this would be 12. So this one they're not coplanar, they're going to be parallel. So this plane and this plane go like this. You're sort of looking at them from the side. This one here, I can't make this from this equation, right? Like double 1 would get 2, double 2 would give you 4, not 5, so that didn't work. So this one is not, it's not parallel to the other two, so it's going to cross something like this. Again, looking at it from the side. So you can see that that's not going to have an intersection. So if I dump this into my Gauss-Jordan, I should end up with one of those impossible rows. So you're going to get it in this one here, right? So 1, 2, 3, 4, 2, 5, negative 3, 2, 3, 6, 9, 11. So I'm going to keep row 1, and then I'm going to do 2 row 1s, subtract row 2, and then I'm going to do 3 row 1s, subtract row 3. So 1, 2, 3, 4. 2 of these would be 2, minus 2 is gone. 4 minus 5 is negative 1. 6 minus negative 3 would be 9, and 8 minus 2 would be 6. 3 minus 3 is gone. 6 minus 6 is gone. 9 minus 9 is gone. And 12 minus 11 is 1. So there it is. There's my impossible row. So I've just figured out then that because these things are proportional, row 1 and row 3, I have 2 parallel planes. And the third one just crosses in between them. Oh, so I guess I should finish. Because there's an impossible row, therefore there's no intersection. All right, so I'm going to try doing some elimination on this one. I've got 8s and 7s in the front. I don't really like that. But if I did 8 minus 7, I get a 1. If I did 8 minus 7, I get a 1. So I'm going to do that just to try and reduce my numbers a little bit. So in my first row of the matrix, I'm going to do R1 minus R2. In the second row, I'm going to do R3 minus R2. And then an 8 minus an 8 will eliminate each other nicely. So I'll do R1 subtract R3. Let's see what we get. So 8 minus 7 is 1. Negative 10 subtract negative 16 is 6. 1 subtract negative 10 is 11. 35 subtract 56 is negative 21. 8 minus 7 is 1. Negative 2 subtract negative 16 would be 14. Yep. 13 subtract negative 10 would be 23. And then 7 subtract 56 would be negative 49. And then 8 minus 8 is gone. Negative 10 subtract negative 2. Negative 10 subtract negative 2 is negative 8. And then 1 subtract 13 is negative 12. 35 subtract 7 is 28. Okay, that's a whole bunch of gross. So I'm going to keep R1. And then I'm going to do R2 subtract R1 in that row. And then I'm going to do a quarter of R3 because these all divide by 4, so maybe I'll shrink them down to get some smaller numbers. It always helps. 1, 6, 11, negative 21. 1 minus 1 is gone. 14 minus 6 is 8. 23 minus 11 is 12. Negative 49. Subtract negative 21 is negative 28. Interesting. So maybe I won't do that. I'm just going to leave R3 R3 was 0, negative 8, negative 12, 28. So this time I'm going to divide that by 4. Keep R1, do a quarter of R2, and in my last slot I'm going to do R2 plus R3. So 1, 6, 11, negative 21, 0, 2, 3, negative 7, and 0, 0, 0, 0. So I have eliminated an entire row. So what does that tell me? Well, it's showing that these 3 planes are going to end up intersecting the same way that 2 planes did. So they're going to end up intersecting on a line. I don't have enough equations now to actually solve all the letters. So I'm going to have to reduce this a little bit and then shove all the z's or all the y's or whatever over to one side and replace them with p to try and build the vector equation of a line. So if this happens to you, that all of that bottom row is zeros, these planes intersect on a line. Okay, so just looking at that, I'm going to take R1 and I'm going to subtract 3 of R2 because that would eliminate my y's here. I'm going to leave R2 alone, and then there is no point in writing R3 because it's been eliminated. So 1 of these minus none is 1. 6 minus 3 of these would be gone. 11 minus 9 would be 2. And negative 21 subtract negative 21 would be 0. This row is 0, 2, 3, negative 7. So pulling that out of the matrix, I have 1x plus 2z's equals 0. And I have 2y's plus 3z's equals negative 7. So if I pull this 2z over here, 0 minus 2z, and the 2y be negative 7 minus 3z. Divide by 1 doesn't change anything. Divide by 2, I get negative 7 halves minus 3 halves z. If I replace z then with my p, so I say let z equal p, then y is negative 7 halves minus 3 halves p, and x is 0 minus 2p. And this would be more convenient if I wrote it as nothing plus 1p. So I've generated the parametric equations of my line. So in vector form, x, y, z equals 0, negative 7 halves, 0, plus p, negative 2, negative 3 halves, 1. Okay, so 3 more planes. I'm going to set into some Gauss-Jordan elimination. I'm going to leave R1 where it is because it has a 1. And then I'm going to take, so leave R1, I'm going to take 5 R1s and subtract R3. And I'm going to take 2 R1s and subtract R2. I got 1, 3, negative 2, negative 5. 5, well, these would be 5 minus 5 is gone. 15 minus negative 2 would be 17. Negative 10 subtract negative 3 would be negative 7. Negative 10 subtract negative 3. Negative 7. 15 minus 2 is 17. Yep. Negative 25 subtract 13 is negative 38. 2 of these would be 2, minus 2 is gone. 6 minus negative 1 is 7. Negative 4 subtract 4 is negative 8. Negative 5, so negative 10 subtract 21 is negative 31. Now those are pretty gross. I'm going to have to do 7 of row 2 and 17 of row 3. So let's do that. I'm going to have to pull out a calculator, I think. Alright, so 7 times 17 is 119. 7 times 7 is negative 49. 7 times 38 is negative 266. 17 times 7 is 119. 17 times 8 is 136. And 17 times 31 is 527. Just check my negatives. Okay. So I'm going to keep R1. I'm going to go back to 1/17 of R3. Because that was this line. That was the cleaner one. Just write that in. 1, 3, negative 2, negative 5. And this row was 0, 7, negative 8, negative 31. 0 minus 0 is 0. 119 minus 119 is gone. Negative 49 subtract negative 136 is 87. And negative 266 subtract negative 527 is 261. Yuck. But we're down to this line where I have an equation here that says 87z equals 261. And if you're real good at numbers, I think you might have already picked out this is 3. 261 divided by 87 is indeed 3. So I could go back and I could use Gauss-Jordan elimination to eradicate the rest of these numbers. So I'm going to do that. I'm going to keep R1. I'm going to keep R2. And then I'm going to have 1/87th of R3. So 1, 3, negative 2, negative 5, 0, 7, negative 8, negative 31, and 0, 0, 1, 3. Okay, so I'm going to take R1 and I'm going to add 2 of R3 to it. And then I'm going to take R2 and I'm going to add 8 of R3 to it. And I'm going to leave R3 alone. So 2 of these plus that would be 1. 2 of these plus that would be 3. 2 of these plus that would be 0 as planned. 2 of these is 6 plus that is 1. 8 of these plus that is 0. 8 of these plus that is 7. 8 of these plus that is 0 as planned. And 8 of these, 3 times 8 is 24. 24 minus 31 is negative 7. So I'm going to take 1/7 of R2 there. And I'm going to add it to, well, no, let's do one thing at a time. Jared, don't get too carried away. 1/7 of R2, and I'm going to leave R3 alone. So 1, 3, 0, 1, 0, 1, 0, minus 1. 1y is negative 1. We've got another number solved. Then I'm going to take R1 and I'm going to subtract 3 R2s. So I have 1, 3 minus 3 of those will be gone. That's gone. 3 minus negative 3 would be 4. So what I've got there is a matrix that's telling me that x equals 4, y equals negative 1, and z equals 3. So these three planes intersect on a nice clean point right at x, at 4, negative 1, 3. So if this happens to you and you get actual values for x, y, and z, they have intersected all on one single point.